Hi student. Now I am continue to the previous lecture. I am discussed a previous lecture. What do you mean by the sequence and what's about and the bounded and unbounded region of a sequence, and also discuss the limit point of the sequence. Now today I am discuss the convergent and divergent sequence. A convergent sequence, if a sequence exists a limit point L in a sequence, the all value of the sequence Sn minus L is always less than the epsilon. Now, first of all, I am discussing the epsilon. Epsilon, there exists a real number of the sequence. It means if any limit point L exists in a sequence as epsilon is greater than 0, the sequence is called a convergent. Now, divergent sequence is if the sequence exists in a plus infinite to minus infinite of a real number k is greater than 0 or a k is less than 0. Now, first of all, I am discussing convergent. Now, you can note down convergent sequence. Convergent sequence. Now, you can note down a sequence Sn is said to be converge at limit point or a real number L or a real number L, there exists a real number M is such that Sn minus L is less than epsilon, where n is greater than equal to m, or you can simply write limit n tends to infinite, Sn is equal to L. Sn is equal to L when Sn tends to L as n tends to infinite. N tends to infinite. A function is known as a convergent. A function is known as a convergent. Now, if, for example, you can note down a sequence 1 upon n is convergent sequence. Now, again discuss the divergent sequence. Now, you can note down a sequence Sn is said to be diverge at plus infinite as a real number k is greater than 0, there exists a positive real number, positive integer, there exists a positive integer positive integer m is such that Sn is greater than k when n is greater than equal to m, or you can say limit n tends to infinite, Sn is equal to infinite plus infinite. If k is less than 0 for diverge minus infinite is such that Sn is less than k as n is greater than equal to m, or you can say limit n tends to infinite, Sn is equal to minus infinite. Sn is equal to minus infinite. There are two more important conditions of the sequence. First is called the convergent and second is called the divergent. Divergent for a positive infinite, divergent for a negative infinite. Now you can note down. You can note down. First of all, you can note down the example. For example, a sequence n is diverge as plus infinite. Now, example number second is minus sequence minus n is diverge as minus infinite. Now you can note down. Next is a oscillatory sequence. Now you can note down oscillatory sequence. Oscillatory sequence. If a sequence neither a convergent nor a divergent, a sequence is known as a oscillatory sequence. Oscillatory sequence mainly two types. First is finite oscillatory sequence, and next is an infinite oscillatory sequence. Because the two type of the sequence, first is a convergent and second is a divergent. Now the definition of this sequence, you can note down a sequence Sn is said to be oscillatory if oscillatory sequence if it is neither convergent neither converge nor diverge, neither convergent nor divergent. A sequence is said oscillatory sequence. There is a two type of the oscillatory sequence. First is, for example, you can note down. First is oscillate finitely. Now you can note down a sequence 1 plus minus 1 to the power n is known as a oscillatory sequence. Now second is oscillate infinite infinite. Now, for example, n minus 1 to the power n is called the oscillate infinite sequence. There is a two example of the oscillate sequence. If n is a natural number, now you can put all the value of n. First is 1, the value is 0. Now second is called 1, 1, 2. When n is equal to 2, you can find 1 plus 1 is equal to 2, 0, 2, 0, 2, 0, 2. This is called the finitely because the all members is belonging to 0 to 1. Now second is a n minus 1 to the power n. When n equal to 1, the value will be find minus 1. Now when n equal to 2, now value will be find when n equal to value is find to 2. Now the two value of the this oscillatory function 1, 2, 1, 2, 1, 2. Now again value putting the 3. This means not defining the above function of this value. Discuss a numerical problem of convergence. First of all, you can read discuss the convergence of the sequence 1 upon 3 to the power n. First of all, you can let the solution of this problem, let a sequence Sn is equal to sequence 1 upon 3 to the power n. Now, to find limit n tends to infinite s to n. Now you can write limit n tends to infinite 1 upon 3 to the power 2n, or you can say the value is 0. If n is equal to infinite, the value is 0. Now second is and find the value of limit. Next value of the limit n tends to infinite s 2n plus 1. You can write limit n tends to infinite 1 upon 3 to the power 2n plus 1. Now again value find the 0 since limit n tends to infinite s n is equal to 0, or you can say the limit n tends to infinite s 2n, or is equal to limit n tends to infinite s 2n plus 1 is equal where all value of n belongs to capital N. Capital N, hence 0 is finite quantity, finite value. Therefore, the sequence 1 upon 3 to the power n is convergent sequence. Hence prove that. Now first of all, you can note down the first numerical related to the convergent sequence. Now I am discuss the next numerical problem related to convergent and divergent. The next topic is Cauchy sequence. You can note down Cauchy sequence. Now you can note down a sequence Sn is said to be Cauchy sequence if a given epsilon is greater than 0, there exists n belongs to capital N. N belongs to capital N is such that mod Sn minus Sm is less than 0. Now you can say m is greater than equal to m, or you can simply write Sn plus P minus Sn is less than 0 when all value of n belongs to m and p is greater than 0. A sequence is said to be Cauchy sequence if the following conditions are fine. Now, some numerical related to the Cauchy sequence, you can note down the example of Cauchy sequence. You can read if Sn is a sequence in R where Sn is equal to 1 plus 1 upon 2 plus 1 upon 3 plus 1 upon n, evaluate limit n tends to infinite Sn plus 1 minus Sn and verify the Cauchy sequence. First of all, you can note down the solution of this problem. Let Sn is equal to 1 plus 1 upon 2 plus 1 upon 3 plus 1 upon n and Sn plus 1 is equal to 1 plus 1 upon 2 plus 1 upon 3 plus 1 upon n plus 1 upon n plus 1. Now, to find then limit n tends to infinite Sn plus 1 minus Sn is equal to 1 upon n plus, sorry, you can write limit n tends to infinite 1 upon n plus 1, or you can say the value of this is equal to 0. Now this is 0 or is equal to 1 upon infinite. Also here we have S2n is equal to 1 plus 1 upon 2 plus 1 upon 3 plus 1 upon n plus 1 upon n plus 1 plus 1 upon n plus 2 plus 1 upon 2n 1 upon 2n. Now limit n tends to infinite as 2n minus Sn is equal to limit n tends to infinite, you can write 1 upon n plus 1 plus 1 upon n plus 2 plus 1 upon 2n, or you can write is less than equal to n limit n tends to infinite n 1 upon 2n, or this is equal to 1 upon 2. Since there exists a number k is greater than 0, then is greater than equal to 1 upon 2 is not satisfied Cauchy sequence. This is a numerical related to the Cauchy sequence. If you have any problem, please comment to my video. Now again I am discuss the monotonic sequence. Now discuss the monotonically sequence. A sequence Sn is said to be monotonically if it is either increasing of monotonically or decreasing monotonically. First of all, I am discuss the monotonically sequence of increasing or decreasing monotonically. First of all, you can note down monotonically sequence. Now you can note down a sequence Sn is said to be monotonically if it is if it is either monotonically increasing monotonically increasing increasing or monotonically monotonically decreasing decreasing now first I have discussed the monotonically increasing. Now you can note down first monotonically monotonically increasing. A sequence Sn, a sequence Sn is said to be is said to be monotonic monotonic increasing if if Sn is less than equal to Sn plus 1, where all value of n belongs to capital N, or you can say Sn is greater than equal to Sm, where all value of n is greater than equal to m. This is called a monotonically increasing. Now in this case number first, strictly monotonic increasing. You can write strictly monotonic increase. You can say a sequence a sequence a sequence Sn is said to be statically increasing if Sn is less than Sn plus 1, where all value of n belongs to capital N, or you can say Sn is less than Sm, where all value of n is greater than equal to m. This is known as the statically increasing, and this is a increasing monotonically sequence. Now, for example, a sequence 2, 2, 4, 4, 5, you can say 6 is monotonic increasing. Now a sequence 1, 2, 3, 4 is known as a statically increasing is statically monotonic statically increasing sequence statically increasing monotonic sequence. It means a sequence Sn is greater than equal to Sn plus 1 when n is belongs to positive integer of natural number. You can say where m is a positive integer, there exists a positive integer. This is equal to, and the statically increasing means if Sn is less than Sn plus 1 for this example. Now next is a monotonic decreasing. You can note down strike monotonic, monotonic, monotonically decreasing, decreasing sequence, sequence. A sequence, a sequence. Sn is said to be, Sn is said to be, said to be monotonic, monotonic decrease, monotonic decrease if Sn is greater than equal to Sn plus 1, Sn plus 1, where all value of n belongs to capital N, or you can say the Sn is greater than equal to Sm, all value of n belongs to small m, there n exists a positive integer. And next is, you can note down, statically decreasing. Now, next is, you can note down the case number second. You can note down statically decreasing, decreasing monotonic, monotonic sequence. You can note down a sequence. Sn is said to be a sequence, a sequence. Sn is said to be, is said to be statically, statically, statically decreasing, decreasing if a sequence, if a sequence, if a sequence Sn is greater than Sn plus 1, well, all value of n belongs to natural number n, or you can say Sn is greater than Sn plus 1, sorry, Sm, all value of n belongs to m, where m exists a positive integer, where there exists m is a positive integer, positive integer, positive integer. For example, for example, for example, a sequence 1, comma 1, comma 1 upon 3, comma 1 upon 3, comma 1 upon 5, comma 1 upon 7, comma 1 upon 8 is monotonic decreasing, monotonic, monotonic decreasing, decreasing. Now, the second case is sequence -2, comma -4, comma -6, comma -8, and now next is statically decreasing, decreasing monotonic sequence, monotonic, monotonic sequence. This is the another two types of the sequence of monotonically. First is monotonic increasing, statically monotonic increasing, and second is monotonic decreasing and monotonic statically monotonic decreasing. Now you can check to this rule. You can check to this rule. This is a condition of the monotonic decreasing, monotonic decreasing, and this case, this is condition for check out the statically monotonic decreasing. Now, if you have any problem related to any topics of the sequence or convergent or divergent, please comments to my video, dual mathematics classes. Now I am solving the more example or your problems. Now to next lecture, please.